Hello, my name is Fred Garber, and I teach EE 2010 and EE 2011, which meets together. The course covers the basics of circuit analysis. So circuits, of course, are the building block of all electronic devices, both on the analog side, so things that you might have in your cell phone that amplifies and produces sound, or communication devices, and on the digital side, consisting of gates and combinations of gates and larger systems that do computational tasks, and other things. So this is sort of the front door of circuit analysis for electrical engineers and other engineers. And we start in the analog world with linear components. So here is a bit of a standalone sound card, and we see some amplifiers and capacitors, those little orange things, and variable resistors, the things with knobs that are working with the amplifiers to adjust gain and maybe some tone, some frequency domain processing. And then resistors, those blue things all over the place with stripes on them. Oh, also these big can things are just larger capacitors, bigger cousins of the orange ones. Similar on a sound card that goes in the back of a desktop. And this happens to be a sound card that is suitable for Dolby systems, which is a recording and playback standard. So there's some digital things going on this card and some analog things going on this card with similar kind of things we see on the card on the right with capacitors, amplifiers, resistors. So that's kind of the context of circuits. And again, circuits are used in every kind of device that has any function whatever. Refrigerators, well, here's an analogy, or maybe a word picture. Circuits are the heartbeat of everything in Best Buy, everything, appliances, gizmos, computers, everything, except the music aisle, where you buy music, and the movie aisle where you buy DVDs or Blu-ray. But even those media are helpless until they're played in a device that is, in both of those cases, have both analog and digital components. So it's a very important foundation, and I think it's very exciting. So in a circuits course, so that what we saw above was pictures of circuits. This is a diagram of a circuit, and this particular one is a very simple transmitter, starting with a microphone. So voice comes in and radio frequency transmission goes out, and it's composed, and now we don't see the physical devices, but we do see the diagram symbols for resistors and capacitors and inductors. Here's a variable capacitor and active elements, transistor. Here's another transistor. And I remember way back before I started down my path in electrical engineering thinking, okay, so here's a junction with 4 paths out of that junction. How does an electron decide which way to move? And all circuits operate by virtue of the movement of electrons. Electrons are charged, and so the movement of charge is flow. And so electrical flow is current, electrical pressure is voltage. And so there is a fluid analogy that's very appropriate for the analysis of circuits. And I can tell you, just looking at this region that I've circled, there are 4 paths out of that region. If this were 4 water pipes connected together, and I told you that if I add up all of the water flow out of that region, it would have to add to 0, which is the same as saying that everything flowing out, there must be from some other source water flowing in, because it has to go somewhere and it cannot appear out of nowhere. So the same is true in circuits. In fact, that little realization that if I add up all the flow out of a region, it has to equal 0, is what's called Kirchhoff's current law, which is the key to unlocking the analysis of virtually every circuit on the planet. So what do we do in this course? We first start off with electrical quantities: voltage, which is electrical pressure; current, which is electrical flow. And we look at models for the elements that we're using, include conservation laws. So I just did an overview for you of the conservation of charge law that says, again, in any region, the flow in equals the flow out, along with some linearity reductions, making things simple, that lead to algebraic expressions that describe a circuit. And we employ a solver, so we're not pretending that computers don't exist, and we're also not pretending that there are not solvers out there. So instead of writing systems of equations and solving them on our own, that only works for fairly simple circuits. But when circuits gets complicated, more components, more connections, we no longer are in the realm where we can by hand approach that. But that's okay. In fact, that's a good thing, because more and more we're using a computer and a solver app or package as an assistant for us to do circuit analysis. And it turns out it's very easy. The human, we use our brains to do the analysis, and then we use the computer to activate the computation. So we are the ones that gain insight and understanding and intuition about the formulation and function and even design and synthesis of a circuit. We use a computer for what it's good at. EE 2010 circuit analysis is done in the format of active learning, where lectures are provided ahead of time, sort of in the mode of the Khan Academy kind of things. Mr. Khan has millions of dollars, and so he probably does some things better than I do. And then backed up with a lab experience to have hands-on either simulation or realization experience. So then the flow is analysis to simulation and then realization. And this is an important flow with analysis and design starting in the first box, because more and more as systems get complicated and expensive, it's much cheaper and easier to do a synthesis, what if, over and over again, change things, try it again, before we go to realization, which is the building of the device. So manufacturers, airplane manufacturers, large, automobile, things that are becoming more and more complex, the human interaction is with the analysis and design and synthesis over and over again, and only when things have been simulated to work perfectly do we do a single build. It's not trial and error, build it, see what works, do it again. The trial and error happens with the analysis, design, and synthesis, simulation. So that's the part that we tackle in this first circuits course. What can you do when you leave this course? Well, here's my statement. Upon completion of this course, you should be able to determine any electrical quantity in any lumped linear analog circuit driven by any excitation. So this is a fairly simple circuit, although right now it may seem a little complicated. I can tell you it's not. We just do one step at a time. We do one part of the circuit at a time. We break it down into steps that are fairly straightforward and methodical. And before we know it, we have described an entire circuit with any excitation, looking at any particular quantity we want. And we're able, again, with the help of a solver, to find that quantity and answer any question we need about that circuit. Well, I hope to see you in EE 2010, EE 2011. It's an exciting course, and we do some, what I think are some fun things and lay the foundation that will be useful for quite some time through your career. Thank you.